Yo, yo. So wanted to do this category theory versus set theory thing. I was kind of curious about this. I've heard before that, well, in functional programming languages like Haskell, category theory is a big deal. And I took this one programming class once, which was on kind of like, it was on like software engineering, weird kind of abstract stuff, like domain driven design or something. And they use category theory in that as well. What I'm wondering is, I never really got a good justification for why they use category theory. What's wrong with just using set theory? Like, what is the limitation of set theory to make it so category theory is like preferred and used in these domains?
That's a great question. The core issue is that set theory focuses on elements and membership, while category theory focuses on relationships, morphisms, and structure. This shift in perspective makes category theory more flexible and better suited for certain applications, especially in functional programming and abstract software design. Limitations of set theory. 1. Rigid element-centric view. Set theory is all about elements and membership, e.g., this object belongs to this set, which is great for classical mathematics, but can be too rigid when dealing with structures and transformations between them. 2. Function representation. In set theory, functions are often just sets of ordered pairs. This works for simple cases, but doesn't naturally capture higher level abstractions like function composition in a general way. 3. Difficulty expressing structure-preserving maps. Many useful concepts in programming and software engineering involve structure-preserving transformations, e.g. functors, monads. Set theory doesn't have built-in ways to capture these, whereas category theory does this naturally. 4. Set theoretic paradoxes and size issues. Set theory struggles with certain infinite constructions and paradoxes, e.g. Russell's paradox. Category theory, by focusing on relationships rather than elements, avoids some of these issues. Why category theory is useful. Focus on structure and composition. Instead of just dealing with objects, category theory emphasizes how objects relate through morphisms, functions. This is why it maps well to functional programming. More general and abstract. Many concepts from set theory can be recovered within category theory, but category theory extends beyond sets to more general mathematical structures, making it more versatile. Better for modeling computation. Functional programming relies heavily on composition, and category theory provides a natural language for expressing composition through functors, monads, and other constructs. This is why in functional programming, Haskell, and abstract software design, e.g. domain-driven design, category theory provides a more natural framework than set theory. It helps reason about transformations, relationships, and composability at a high level without getting bogged down in element-level details. Did your class use category theory in a way that seemed practical, or did it feel more theoretical and abstract?
Okay. Can you give me one example of something in functional programming, I guess, and kind of define it or explain it in set theory and also in category theory, and kind of illustrate maybe the example, do it so that it's really nice or elegant with category theory, but it's kind of awkward with set theory. Yeah.
Sure. A great example is monads, which are fundamental in functional programming, especially in Haskell. Let's define and compare monads in set theory and category theory. The example, the maybe monad, used for handling optional values. In Haskell, the maybe monad is a common way to handle computations that might fail. It can be thought of as just x represents a successful computation with a value x. Nothing represents failure or absence of a value. Set theory approach.
Oh, I kind of forgot what monads are. What happened? This book was, yeah, read it for free online. Oh no, they took away all the nice formatting and stuff. Oh, it doesn't look nice anymore. Maybe let me see. There's
While programming, you often need to convert one value into another by applying multiple operations one after the other. Let's visualize this as a pipeline where we apply successive function calls with the return value of each being the input of the next. Take this JavaScript example where we want to make a database query about a user, then get the gender of their best friend. In this case, any one of these functions could fail, such as if the database is down or if the user has no friends, or even if their best friend doesn't have a gender. Assuming that a failure results in null value, it could be problematic passing a null into a function that expects something else. To remedy, you would probably add a bunch of checks after each function call, but this is verbose and quite frankly, ugly. It also makes this code very hard to read since you focus more on the implementation details than the actual operation. To refactor, let's create a class called maybe. Its constructor will simply take a value and store it inside the object instance. We'll also give this class a method called bind, which takes a function.
I kind of want to see like the more mathematical version. Maybe there's maybe Computer File has a video on it.
So monads are a concept that was invented in mathematics in the 1960s, and then it was rediscovered in computer science in the 1990s. And what it gives you is a new way of thinking about programming with effects. And for me, this is one of the most important new ideas in programming languages in the last 25 years. So that's what we're going to be looking at today, programming with monads. I'm going to come at this using a simple example. And the example that we're going to look at is the idea of writing a function that evaluates simple expressions. And we're going to use Haskell for this, but it doesn't matter if you don't know anything about Haskell, because we're going to use it in a very simple way, and I'm going to explain everything as we're going along. So what we're going to start with is by defining a simple data type for the kind of expressions that we're going to be evaluating. So we'll use the data keyword in Haskell, which introduces a new data type. And then we're going to define the new data type for expressions. And then there's two things that an expression can be. It can either be an integer value, so we'll write that down, we have val of an int, or it can be the division of two sub-expressions. So we've got two constructors here in our data type. We've got val, which builds expressions from integers.
Shoot. Come on. I get confused what all these different things are. New algebraic data type. New type. I always like forget this. Like I had I took notes maybe I took notes a while ago on Haskell stuff when I was going through it. I think it was here. Yeah, this stuff. It's annoying. It's like so many of these. Just add a second monitor. So we got value constructor. Confusing. Type constructor. Type synonym. Is that it? Type classes. Got number one. Value constructor. So this is a type. It's like a new type. Okay, so I guess if you just separate these by spaces, it's like these are the. Oh no, this is like this is like just a tuple with these types. Okay. And then you've got a value constructor. These are the different values that it can take on. You did data shape in both these cases. This. These are different values. These are different like types. And then point float is value constructor. Seems similar to this one. Okay, now you do data, maybe it's a type constructor. This is a type and a value constructor. It's a type constructor. This gives you, okay. So before this was like a type and the thing over here was a value. And these are different values. And this is a type and these are different values again. But this is a type constructor, and these over here are types. Makes sense. And then you got a type. I think this is just like an alias. Yeah, okay. So let's see if we can go back here. So you're saying data. So this is it's the type. It's like defining a new type, and it can be one of these two things. Val int. Yeah. So data is a keyword used to define a new type. Okay. New type. It's the name of the new type. Okay, val int. Val is a constructor. It's a function that takes an int and returns an expression. Built-in type for integers, val int. Val 5. Defining it here ourselves. Constructors that create values of type expr. Constructor function that takes an int and returns an expression. Okay, so I mean val it's just something we just completely just made up. And div is just something that we completely made up. This is like a recursive thing. Yo, why is he using such like a complicated example, like just for his first thing? It's like, what the heck? It's crazy, man. Okay.
We've got two B to type keyword, the kind of. So what we're going to start with is by defining a simple data type for the kind of expressions that we're going to be evaluating. So we'll use the data keyword in Haskell, which introduces a new data type. And then we're going to define the new data type for expressions. And then there's two things that an expression can be. It can either be an integer value, so we'll write that down, so we have val of an int, or it can be the division of two sub-expressions. So we've got two constructors here in our data type. We've got val, which builds expressions from integers, and we've got div, which builds expressions from two sub-expressions. So just to reiterate what's actually going on here, we're declaring a new data type called expr, and it's got two new constructors, one called val, which takes an integer parameter, and one called div, which takes two sub-expressions as parameters as well. So basically what we're working with is...
It's almost like just kind of writing it a little bit in Python. It would kind of almost be like... kind of be like a class expression like this. And it'd almost be like val. So and this takes an int. I mean, kind of almost say like I guess these are kind of like this thing is like a class here. Oops. And we kind of like, this takes like an int. What do you want to call it? Almost like num or something. Let's say self.num. And then you've got kind of like a, oops. Got kind of like a div thing here, and it takes in two expressions. And it's almost like this is the division of two expressions. So it'd kind of be like, kind of like that. And then I don't quite know how to define this part right now in Python. It is an expression. I don't know how it like inheritance works or whatever in Python, but I don't know.
Two sub-expressions as parameters as well. So basically what we're working with is expressions that are built up from integer values using a simple division operator. So many of you may not be familiar.
Oh, why he didn't just do
value. So
expression is equal to the division of no, I didn't just do it. Just like two ints or something. Two ints.
So what we're working with,
like div int. Yeah.
Is expressions that are built up from integer values using a simple division operator. So many of you may not be familiar with this kind of syntax. So let's have a couple of examples of values of this data type so that we make sure everyone's on the same page. So what I'm going to do here is draw a little table. So on one side, on the left-hand side, I'm going to have what we would normally write down in mathematics. And then on the right-hand side, we'll think, how would you translate this into a value in this Haskell data type? So let's have three simple examples here. We'll have 1, and we'll have 6 divided by 2. And let's do one more example. We'll have 6 divided by 3 divided by 1. So these are simple expressions built up from integers using a division operator. But we're writing Haskell programs today. So let's think, how do these things actually get represented as values of our expression data type? So the first one is very simple. If we want to represent the value 1, we just need to use...
Would you just do, I don't know, I'm just kind of guessing. Would you just do like the value 1? Would you just say, I don't know if you do like EXPR of 1, or if you do like EXPR a val of 1, or you just do like a val of 1. Maybe something like this.
Val tag. So we write val of 1. If we want to have an expression like 6 divided by 2,
6 divided by 2. I guess it's div of 6 and 2.
well, it's a division. So we have a div at the top level, and then we have two values. We have val 6 and val 2. And actually, I'll leave the last one as a little exercise for you here. So you can try this one for yourself. How do you represent this as a value in Haskell? Well, you're going to need two divisions.
I guess this is like a div of 3 and 1, and then like a div of 3 and that kind of thing.
You're going to need 3 val constructors and then a bunch of brackets. So this is the basic idea. We've got simple expressions built up from integers using division, and we want to think about how do we write a program to evaluate these expressions. Let's write a program to do that. So we're going to write an evaluator, and it's going to be a program or a function in this case that takes an expression as input, and what it's going to give back is the
almost kind of like just want to like go through this like this. Yeah, it's pretty long. Dang, man. Maybe like the Wikipedia page. category theory, functional programming. I want this. Example, maybe constructor. So if I remember kind of the notes I was taking at the time and stuff, it was like I was kind of thinking of monads as oh no. Okay, there we go. Kind of thinking of monads as like it's almost like I think I was thinking of it like a box. I guess I don't know if you just got like the raw value 5, then a monad of 5 is kind of like it's kind of almost like a box with like a 5 in it. And so instead of just passing around like the raw value of 5, you pass around this box. And what can you ask of this box? You can ask like, hey, give me the value inside this box. And the box might not have anything in it. So it just kind of returns like null or whatever. Or if it does have a 5 in it, it'll just like give you a 5. So you kind of like have 5, but then you create a monad out of that, and now you pass around this M5 of thing instead. Wraps it in a monadic value of type M of A. This bind thing, it takes in a monad, and yeah, I don't know. It takes in two things, I guess. It takes in like a monad and a function which takes in an A and gives you a monad of B, and does a monad of, yeah, it gives you a monad of B. Receives that and accepts values of type, unwraps A, applies F to it. And then produce this. Pipeline, several bind operators. Return, yeah, so it starts with a value of A and gives you a monad of A. So just kind of writing this one out. So this bind function here takes in a monad, basically takes in a monad. And it also takes in a thing that kind of maps A to, takes in a function which maps A to monad B. and gives you a monad of B. I guess A and B don't necessarily have to be the same type. So you could go from like a monad of like ints to like a monad of floats. Pipelines, several bind operations. Each function call transforms its plane. Bind operator. Can inject into the monadic value MA some additional information that is not accessible within the function of F. Pass it down the pipeline. Can exert finer control. Okay. Maybe, let's see, undefined particular pain point, null, this causes bugs, just deal with these, explicitly defining two states of a result, just this or nothing. Example, directing a parser, turn an result, or else with just a little extra functional spice on top. Dang, getting sassy, getting fancy. This maybe type transforms into a fully featured monad. Most languages, maybe monad option, just a type that marks whether it contains a value or not. Enumerated type. Oh no, the Rust people have taken over. They've like, I feel like this, it's unfortunate. I feel like this page used to have Haskell for examples, but now there's stupid Rust. Maybe wrapping. This thing here is just like this is like a type constructor, pretty much like we saw in Haskell. It's a type constructor. Maybe type is used as a result of functions that may fail, divide by 0. So takes in 2 decimals and returns a maybe decimal. So in this case, you just return, so you return a maybe decimal. So you either return nothing or you return just a thing. Okay. One such way to test whether or not a maybe contains a value is to use if statements. So you do this division, and then if guess this is testing to see if it's of a just type thing. Yeah. Pattern match result. So basically just testing to see if it's, yeah. Can compose functions that return maybe, putting them together. Concrete example might have one function take in several maybe parameters and return a single maybe whose value is nothing when any of the parameters are nothing. So you take in two maybes and you return a maybe. And so basically, if both of them are a value, if both of them have values in them, then you just do the normal logic. Otherwise, you just return nothing. Instead of repeating just, we can use something called bind. Takes a monad and a function that returns a monad and runs the function on the inner value, pass monad, returning monad. So what are we doing here? We have maybe, so we're defining a just, and then we do maybe x dot map, add one to it, dot map. Yeah. Bind, more elegant. Have is a function that takes in an int and returns a maybe an int. So yeah, if it's even, then okay. So if you have an odd number, it just doesn't. It's just not defined, I guess. So we're having x. Wait, what? This is the first thing where I'm confused. What's the order of operations of this? So this have is just a function. I guess it's taking in this argument here. So you're doing x. What is x? I'm confused. Let's see. That's fine. Yep, takes an integer. If it's, yep, okay, that's fine. What does this do? If m is equal to just an a, apply f of a. If m is equal to nothing, then return nothing. So x is equal to 8. So you have the 8 and then you do it to have. Okay, so this is like halving something twice. Okay, so you have this and then you do it into halve again. Okay, so that's kind of what's special about this because halve takes in an x. Halve just takes in like a normal int. But this halve x here this gives you a maybe, but then you can just like feed it into the have function again. So basically like halve, yeah, it takes in an int and returns a monad. And now, so we basically have our function here, halve kind of only takes in an int, but with this operator, now halve kind of like takes in a maybe int. We've like we haven't transformed halve, but this bind operator is doing some work to make it so that we can use halve with monads now, whereas before we could just use it with ints. Chainable division. Chainable division. This is even like, what even is this? This is just pseudocode, like at this point. Chainable division is like two monads that get passed in, and so you, oh my god, I can't you just like can't read this at all. What? It's basically a monad, but to be more concise, strict list of qualities: monadic type, unit, bind. Okay.
Integer value of that expression. And there's going to be two cases here because we have two kinds of expressions. We have a case for values. We need to figure out what to do with that, which we'll do in a moment. And then we have a case for division, and we need to think what to do with that. So we've got the skeleton here of our program, and now we just need to fill in the details. So how do you evaluate an integer value? Well, that's very simple. You just give back the number. So if I had val of 1, its value is just 1. And then how do I evaluate a division? Well, these two expressions here, x and y, these can be as complicated as you wish. So we need to evaluate these recursively. So what we would do is evaluate the first one, x, and that will give us an integer. And then we'll evaluate the second one, y, and that will give us another integer. And then all we need to do is divide one by the other. So this is a nice simple program that evaluates these kind of expressions built up from integers using division. We just have a simple recursive program, two cases, and everything looks fine. But there's a problem with this program, and the problem is that it may crash, because if you divide a number by 0, then that's undefined, so this program will just crash. So in particular, if the value of the expression y here was 0, then this division operator would crash, and you get some kind of runtime error. So we don't want our programs to crash. So we think, what do we do to fix this problem? First of all, what we're going to do is we're going to define a safe version of the division operator, which doesn't crash anymore, because that's basically the root of the problem here. Division by 0 gives an undefined result, and the program's going to crash. So let's define a safe version of the division operator. We're going to define a function called safediv, and it's going to take a couple of integers, and it's going to give back maybe an integer. And maybe is the way that we deal with things that can possibly fail in Haskell. So the type here is not int to int to int, it's int to maybe int, because division may fail. And we'll see how this maybe type works in a moment. So how do we actually define safediv? We take two integers, n and m, and then what we'll do is check, is the second of these 0? Because that's the case when things would go wrong.
Okay.
So if m happened to...
Yeah, okay. So yeah, I can get kind of the basic idea of a monad. So let's see here. We asked that question. We said, Yeah, category thing. We said, all right, give us an example. Sure, monads. Sure, fundamental. Maybe monad. Just nothing. Set theory, we could model maybe as the set. The heck? Nothing. Okay. Okay. So this is nothing. No. It's a function from A to this defined as return. Okay, so return just pulls the value out of the monad. Wait. Goes from A to this. I feel like this is backwards. Like it should go from this to A. Bind monad. Okay, so if we just pass in, yeah, basically that, then it's nothing. Otherwise, we pull it out and we call the function. Okay, we're handling this as a special case. Model maybe as a functor, maybe as a functor. So before we had maybe as a function. Confused. Okay, so you're thinking of maybe as basically like a big set where it's kind of like the union between, okay, A is kind of like all the values that the type could take on, like plus null, nothing basically. So yeah, this return thing I think is backwards, but yeah, okay, so we're checking there. So it's kind of like what we were defining maybe A as the set. So so maybe you were kind of thinking of A as, this your set. Let's just say it's like the set of positive numbers. But then now you have like, this is a type, I guess. And now you have like maybe if A is equal to basically like null plus all these other possible types. But in this, I guess maybe before was a set, but maybe here is going to be a functor. Endofunctor. The category of Haskell types and functions. Here's where, okay. How about you lost me at endofunctor. Functor, structure that maps objects and functions from one category to another. Functor. Wraps values. There may be functor. I'm confused. What is the difference? What's the difference between a monad and a functor? Monad. Functor only applies functions to value sequencing. Functor, just apply a function. A functor allows you to apply a function inside a wrapper, but it does not let functions change the structure itself, maybe as a functor. I gotta go over what functors are again. No. Functors are functional programming kind of thing. Type class, the functor type class represents the mathematical functor mapping between categories. Context is category theory. In practice, functor presents a type that can be mapped over. Applicative functor. Applicative functor. Plick, plick, plick. Is it this, the functor type class? Basically for things that can be mapped over. Okay, so, oh yeah, functor is like, okay, so if you define your thing as a functor, you're saying like, I can be mapped over. So it's basically just like you're saying that you're a collection and that you can be mapped over. Probably thinking about lists, since mapping over lists is such a dominant idiom. List type is part of the functor type class. Better way. It's a class. I forget what a class is in Haskell. Functor where, it's got an fmap thing where you take a function that goes from A to B and what is this? It's like, it's like a function that takes in an A and a function that takes in a B. I'm confused. Maybe ask feel like maybe I'm I'm hitting my limit a little bit here. Maybe not though. How about give me an example of functor? List. Oh my god, this is like, it's either the empty or like, I don't know. Is a non-empty list making blah an instance of functor? Kind of like implementing the functor where, okay, fmap, you're not even using the function, and then it's like you apply the first thing and then you apply, and then you do fmap of the rest. Okay. Infix version of fmap. Crazy. Functors, okay, so now it's inside that wrapper. Maybe functor. Okay, so it's kind of, yeah, so yeah, the maybe is a functor because it can be mapped over, but the mapping thing is like just mapping over this like box. It's just like, it's like the simplest version of a collection, just a collection with like 1 or 0 things in it. Endo functor is just a functor that maps within the same category. Okay, cool. Maps between 2 different categories. So the functor, I don't know, maybe the functor is like, the functor is like lists. It's like a list of natural numbers to like a list of real numbers or something like that. If you like do the like inverse square root or something. But the ender functor is just like natural numbers to like natural numbers, say. There's some weird notation for that. Like you wouldn't say like n sub 3, you kind of say like n sub star, where it's like, it's kind of like the power set of, not the, it's kind of like, I don't know, it's kind of like the union over I equals 1 up to like infinity of like n sub I. I don't know. It's like everything. I don't know. Okay. Okay. Set theory. Okay. Category theory. Maybe we model maybe as a functor and a monad. Okay. Okay. Maybe functor. Model maybe as a functor. Maybe as a functor. Maybe is just, so maybe says maybe is a functor is equal to maybe is something that can be mapped over maybe as a functor and we model maybe as a functor and a monad. Maybe as an endofunctor. The category of Haskell types and functions acts on oh my god. Structure preserving. All right, I'm starting to get a little bit of a feel for it, but say I'm like kind of far away from. It's like starting to feel it. Like, yeah, it said that set theory is all about set and set memberships. I don't know when it says like. Come on, ChatGPT. Come on. When you said that set theory is all about sets and set membership, and then you said kind of like category theory is all about like categories and like mappings between categories, I feel it's being a little bit disingenuous because I feel like in set theory, functions are a very key part of that as well. It's kind of like mapping between sets. So I'm a little miffed by that comparison.
That's a great point. Set theory does indeed deal with functions, mappings between sets, and functions play a crucial role in set theoretic mathematics. So let's refine the comparison in a way that better reflects the difference between set theory and category theory. 1. Set theory, elements and functions. In set theory, we describe things primarily in terms of elements belonging to sets, functions that map elements from one set to another. Example in set theory, let's say we have two sets, a equals 1, 2, 3, quad b equals a, b, c. A function f a to b might be f of 1 equals a equals b, quad f of 3 equals c. Here, functions are defined by explicitly describing how they act on individual elements. So while set theory does involve mappings, these mappings are always described in terms of elements. The focus is still on what's inside the sets. 2. Category theory, objects and morphisms. In category theory, we shift the focus from elements to structures and transformations. Instead of talking about sets and their elements, we talk about objects, which could be sets, but also types, spaces, etc. Morphisms, which represent relationships between objects, not just functions between elements. Hashashed example in category theory. Instead of saying set A contains the elements 1, 2, 3, we say A and B are objects. 9SF A to B is a morphism between them. We don't care what's inside A or B, only that there is a way to go from A to B. This makes category theory more abstract than set theory. It's about how objects relate to each other rather than what they contain. 3. The key difference, feature, set theory, traditional, category theory. Focus, elements and sets, objects plus morphisms. Functions, explicit mappings of elements, structure preserving transformations. Composition, defined element-wise, defined abstractly using composition rules. Example, f of x equals x squared on real numbers, f a to b, without mentioning elements. In set theory, we always refer back to elements. In category theory, we abstract away the elements and focus only on how objects are connected. Why category theory? The power of category theory comes from composition and structure preserving properties. In functional programming, we use functors, monads, etc. to model computations, and these are defined purely in terms of structure and composition. In mathematics, category theory provides a unifying language across different fields, from algebra to topology. Final thoughts? You're absolutely right that functions exist in set theory, and they do play a major role. The key distinction is that in set theory, functions are defined in terms of elements, while in category theory, morphisms are abstracted from elements and focus on composition. Does this new framing make more sense?
Is there like a single motivating example for that illustrates when it's nicer to frame something in terms of category theory versus set theory?
Yes. A single powerful example where category theory is much nicer than set theory is the concept of natural transformations in functors, especially when dealing with computations or algebraic structures that involve transformations between different representations. A concrete programming-related case is list reversal and why viewing it categorically makes things cleaner. Example, reversing a list in set theory versus category theory. Set theoretic perspective, element focused. If we think purely in set theory, a list is just a set of elements, and reversing it means manipulating those elements explicitly. We define a function. You can see the code in our conversation history. Here's what happens. We take elements one by one. We apply operations that refer directly to those elements, concatenation plus plus. The problem? This description only works for lists. We need a different function for trees, arrays, etc. It's tied to elements, meaning we must redefine things explicitly for each data type. Category theoretic perspective, structure focused. Instead of focusing on elements, category theory asks, what is a general operation that reverses structure, no matter what kind of sequence we're working with? We can describe reverse as a functor transformation. There's a functor that represents a sequence of things, e.g. list. There's a transformation from this functor to itself that reverses order without caring about the elements. In category theory, this is a natural transformation. Eta, F, right arrow G, where F and G are both functors from types to types, list to list, and Y eta is the function reverse. Now we can generalize this to any structure that preserves order, not just lists. Trees, tree A, where left and right subtrees swap. Stacks, push to front versus push to back. Streams, flipping an audio sample sequence. Sequences, reversing a transformation pipeline. Instead of redefining reverse for each case, we can think of it as a morphism in a category. Why category theory wins here? Feature set theory, element focus. Category theory, structure focus. Needs separate definitions. Definition manipulates elements directly, defines a transformation between structures. Reusability needs separate definitions for lists, trees, etc. Works generically for any functor. Abstraction, low, tied to elements. High, only cares about relationships. Generalization, hard to extend, works for all functors. With category theory, reverse is not just an operation on lists. It becomes a pattern of transformation across all sequential structures. So, when is category theory better? Category theory shines when 1, you care about structure more than elements. Example, reverse applies to any ordered structure, not just lists. 2, you want a general reusable concept. FMAP works for all functors, not just lists. 3, you want to compose things easily. In set theory, reverse map FXS requires checking if map or reverse is applied first. In category theory, functors and transformations compose naturally. Final thought. Set theory is great for talking about individual elements and how they relate inside sets. Category theory is better when we care about entire structures and their transformations. Would you like another example, maybe related to monads or error handling?
Interesting. That's all right. I'm getting there. Interesting. Okay. All right. That was interesting. I'll see you guys later. Peace.